Welcome to this next video in the playlist on vector spaces. In this video what we're going to talk about is coordinate vectors with respect to a basis. Okay, now we've already actually discussed this topic in the video on bases of a vector space. However, it's so important to applied mathematics that I think it's worth having a separate video to go over it again. Okay, so what I'm going to do then is firstly I'm going to just do our normal warm-up, remind us all of what a vector space actually is so that we've got a nice picture in front of us of exactly what we're working with, and then we'll go through the definition of what a coordinate vector is with respect to a certain basis. Okay, right. So firstly then, we are going to be working with an abstract vector space, capital V, over some abstract field, capital F. Okay, and I'll remind you of what this actually is. Okay, so a vector space, capital V, fundamentally it is just a set of symbols. It starts its life off as just a set of symbols, so I'll draw this like so. So this box will represent our set of symbols that are going to form the vector space, capital V. Okay, so all the symbols in here are going to be called vectors, and I can just make them up. They're just arbitrary symbols. You can make up whatever symbols you like. That's the fun bit. Okay, so this is just a set of symbols. Okay, now to promote this set of symbols up from just being a set of symbols to being an interesting algebraic study that, an interesting algebraic object that warrants study, what we need to do is define composition laws on it. Okay, and for a vector space over a field F, we are going to define two composition laws. So let's begin with the first one. So the first composition law that we're going to define is going to be called addition. Okay, and what this will involve doing is creating a great big addition composition table like the one that I'm drawing here. Okay, so I'll colour this addition composition table in orange here. Now, this first composition law of addition is going to be a composition law that involves elements of the vector space being composed with other elements of the vector space. Okay, so what I will do is I will put all of the elements of the vector space down here. I will give every single element of the vector space a row in this addition composition table. So I'll colour this in red here. So every single element of the vector space is going to be given a row that is dedicated just to it. So all of the titles of the rows in this composition table are going to be given to vectors in the vector space. And similarly, all of the titles of the columns up here are going to be devoted to elements of the vector space as well. So I'll give every single element of the vector space a column that is dedicated just to it as well. Then what I will have to do is go through and actually define all of the entries in this great big addition composition table. And then later on, if I want to look up what two elements of the vector space added together are equal to, so let's say little v plus little v bar here, if I want to look up what actually is this, well, I go to my addition composition table which defines what this is going to be equal to, okay, and I take the column dedicated to little v, so here let's say this is the column dedicated to little v, and I will colour code it in here. So let's colour code the column the row dedicated to little v here in pink. So I'll take the row dedicated to little v here, which is colour coded in pink. I will take the column dedicated to little v bar, which is up here, okay, and I will colour code that as well. We'll have that colour coded in turquoise here. And then where these two rows and columns interact, okay, or intersect rather, here, this entry of the composition table, this will tell me what the answer to v plus v bar is actually going to equal. So there will be some entry from the vector space here which is sitting in this box here, and that will be the answer to what v plus v bar is. Okay, so I have to go through and define what every combination of two elements of the vector space added together is actually going to be equal to. Now, in order for the vector space to be something interesting to study, you can't just make up this addition composition table arbitrarily. Okay, you can if you want to, but you won't end up with a vector space. You won't end up with an interesting algebraic object. Okay, in order for this to actually end up as an interesting algebraic object that warrants study, it has to obey a bunch of beautiful properties that allow us to do interesting manipulations and prove interesting theorems about it. Okay, and the properties that we insist the addition composition law obeys can be summarized up by saying that this composition law needs to obey the axioms of an abelian group. Okay, so there are 5 axioms that an abelian group must satisfy, and those are the axioms that we're going to insist that our addition composition law obeys for a vector space. Okay, right. Now what we're going to do is define a second composition law on this set of symbols, and that will turn this into a vector space. Okay, so the second composition law that we're going to define is going to be called scalar multiplication. Okay, and it will be given the symbol times, like so. Okay, and I'll colour scalar multiplication's composition table in red here. Now, scalar multiplication is very different from addition because it's not going to involve adding one vector to another vector. Instead, it's going to involve composing an element of the field, capital F, with an element of the vector space, capital V. So indeed, what we're actually going to do to produce this scalar multiplication composition table is we're going to put all of the elements of the field down here. Okay, so we're going to give all of the elements of the field rows that are dedicated to them. Okay, so all of the titles of the rows will be filled up with an element of the field. And then for the columns, they're going to be dedicated to elements of the vector space. So we'll put all of the elements of the vector space up here. We'll give every element of the vector space a column that is dedicated to it. Then what we can go through and do is define what any element of the field scalar multiplied by any vector in the vector space is going to be equal to, and that will just involve filling in this great big scalar multiplication composition table here. Okay, so quite simply, if you want to know what is some scalar or some element of the field C, scalar multiplied by a vector in the vector space, little v, what you do is you take the row corresponding to the scalar little c. Okay, so here's the scalar element of the field, little c. So I'll colour that in purple here. So here's its row. And then what you do is you take the column dedicated to little v. So here is the column dedicated to little v, and then of course where they intersect, that box there will contain the answer as to what c times v is equal to. And the answers in this scalar multiplication composition table will all be elements of the vector space capital V. Okay, right. Now, again, that scalar multiplication composition table, you can't just define the entries arbitrarily. If you want it to be a vector space, it has to obey beautiful properties. Again, those beautiful properties are summarized in 4 axioms that we want it to obey. Axiom number 1 is closure, which says that all of the answers in here have to be back within the vector space capital V, so none of the answers can just be silly symbols that you've just made up, which are outside of the vector space. Okay. Axiom number 2 is associativity, which says that scalar multiplication must associate with multiplication in the field. Axiom number 3 concerns the multiplicative identity of the field and says that the multiplicative identity of the field must scalar multiply any vector in the vector space to give that vector in the vector space back again. And finally, axiom number 4 has 2 distributive laws that we want scalar multiplication to obey. So we want scalar multiplication to distribute over addition in the vector space, and we also want it to actually distribute over addition in the field. Okay, and if you want to go through the axioms of a vector space more properly, watch my video on the definition of a vector space. Okay, so there's our warm-up. We now have a nice picture of our vector space V over the field capital F. Okay, right, so now let's actually begin with the topic of coordinate vectors with respect to a basis. Okay, so for the basis of this video then, we are going to be working with a finite dimensional vector space. these concepts can be extended to the topic of infinite dimensional vector spaces, but it's not something that is done in algebra. Instead, it's something that's done in analysis. Okay, so you need analytic concepts to be able to extend it to infinite dimensional vector spaces. So we're not going to touch infinite dimensional vector spaces, we're just going to look at this for finite dimensional vector spaces. So that's going to be our first assumption, that V is finite dimensional. Okay, and I'll remind you that being finite dimensional means that there is a finite set of vectors from the vector space capital V which completely spans the vector space capital V. Okay, now we know that the instant it's finite dimensional, what it means is that you can always find a basis. So we proved this in the previous video in this playlist on finite dimensional vector spaces, that once a vector space is finite dimensional, you can always find a basis for that finite dimensional vector space. And moreover, if you have another basis of that finite dimensional vector space, it will have exactly the same number of vectors within it. And that number of vectors that any basis of a finite dimensional vector space will contain is what's called the dimension of that vector space. Okay, so let's write some of that down. So what we're going to do then is we're going to find some basis of our vector space, which we can always do if it's finite dimensional. And I'll remind you that a basis of a vector space is a subset of the elements of that vector space, which contains a finite number of elements. So we'll have v1, v2, all the way up to vn, okay, where n is the dimension of the vector space, this constant that is associated with any finite dimensional vector space. Okay, so all of these vectors in this set are just elements of the vector space. So to make this utterly explicit, I'll just put them on here. v1, v2, they're all in this great big set, and then we'll have vn. Okay, so they're all just vectors from our vector space, symbols from our set over there. Okay, now this, to be a basis, this set of symbols has to obey two incredible properties. Okay, and these two incredible properties are that it must span the entire vector space and it must be linearly independent. Now let me just remind you what those two things mean and what together they mean. Okay, so number one is that the span of this basis, the span of this set of vectors, must equal the entire vector space. So span B must equal the entire vector space, capital V. Okay, right. Now what does that actually mean? Well, of course, we need to know what the span of a set of vectors actually is equal to. And I'll remind you that that means the set containing all linear combinations of the vectors in this set, capital B. So it means all things of the form c1 times v1 plus c2 times v2 plus all the way up until you get to cn times vn, where the ci's are elements of the field, capital F. Okay, so what you're doing here then is you are letting these elements of the field, c1, c2, all the way up to cn, you are letting them vary over every element of the field. So in this position, you put in every element of the field. For every element of the field that you put in that position, you let C2 vary over every element of the field. For every combination C1 and C2 of elements of the field, you let C3 vary over every element of the field, and so on and so on. You take every possible combination of elements of the field you can. You construct this great big sum here. So you're scalar multiplying all of these basis vectors by elements of the field to get new elements of the vector space, and then you're adding all of those new elements of the vector space together to get some final element of the vector space. Okay, so this great big sum, this linear combination as it's called of the basis vectors, this will be some other element of the vector space, capital V. Okay, right, so you take every possible thing of this form, you construct every single last one, okay, and you stick them all into a set, and this set is what's called the span of that set of vectors B. Now, if this is a basis, then it has to have the special property that every single vector is going to be hit at some point. So some combination of elements of the field will produce you any vector you like from the vector space. Okay, so this is going to contain the entire set of elements from the vector space, i.e. all vectors in the vector space can be written as a linear combination of the basis vectors. Okay, so that's property number 1 that we want a basis to obey. The other property that we want it to obey is that it's going to be linearly independent, Li. Okay, now I'll remind you of what linearly independent means. So linearly independent means that there is only one linear combination of the vectors in the basis which will actually give you the 0 vector. Okay, so I'll just write out a linear combination here, c1 v1 plus c2 v2 plus all the way up until we get to cn vn. Okay, if it's going to be linearly independent, then the only solution to this equation that the linear combination is equal to the 0 vector within the vector space, the additive identity within the vector space, is if all of these coefficients are equal to 0. Okay, so all of these coefficients are 0 in the field. So c1, c2, all the way up to cn, we need them all to be 0. Now, of course, this is always a solution. Okay, so it will always be the case that if you set all of these equal to 0 and take that linear combination of these vectors, v1, v2, all the way up to vn, that you will get the 0 vector, but we want that to be the only linear combination of these vectors, v1, v2, all the way up to vn, which gives the 0 vector. Okay, and that then is the requirement for a set of vectors to be linearly independent. Now, the incredible thing then that linearly independence actually gives rise to is it means that if you take any two different linear combinations of the vectors v1, v2, all the way up to vn, that they are not going to be the same answer within the vector space. So what do I mean by that? I mean that each element of the vector space has only one linear combination which gives rise to it. Okay, so the instant you insist that the 0 vector has only one linear combination of these vectors that gives rise to it, it then becomes the same for all other vectors in the vector space, i.e. all other vectors in the vector space have only one linear combination of the vectors v1, v2, all the way up to vn, which actually gives rise to them. Okay, so what this now overall means is that if I have some arbitrary vector in my vector space, so let little v be an element of my vector space, capital V, I can now write little v as a linear combination of these basis vectors. Okay, I can do that because of course the basis spans the entire vector space, so I can write any vector in the vector space as a linear combination of the basis vectors. But now the linearly independent property tells me that this is unique, that there is only one linear combination of these basis vectors that actually gives this vector v. Okay, so I have got the one and only one linear combination of these vectors which actually gives v. Okay, so now these two properties together mean that a basis for a vector space is a set of vectors such that you can write any vector in the vector space as one and only one linear combination of those basis vectors. Okay, right. So that's the thing then that we need to discuss in order to actually discuss coordinate vectors. Okay, so now that we've got the concept of a basis, we are ready then to actually see the concept of coordinate vectors with respect to a basis. Okay, so this is the great idea then. At the moment, this vector space here is extremely abstract. It's just an abstract set of symbols with these abstract addition and scalar multiplication composition laws on it. Okay, they could have very silly symbols that we are not familiar with here. Okay, what we can now do, if it's a finite dimensional vector space, we can find a basis for that finite dimensional vector space, and we can use this basis to give every single vector in the vector space coordinate vectors with respect to that basis. We can give every single vector in the vector space coordinates with respect to the basis. Okay, a beautiful symbol to represent it, a beautiful, nice, intuitive symbol to represent it, rather than potentially the silly abstract symbol that it's got at the moment. Okay, so what beautiful intuitive symbol are we going to give each vector? Well, here's my vector little v, an arbitrary vector from my vector space. Okay, I've written it as this one and only one linear combination of the basis vectors, v1, v2, all the way up to vn. And we've got some scalars in front of here. Okay, we've got c1, c2, all the way up to cn here, and these are specific scalars that are specific to this vector v. Okay, so we could associate this combination of scalars from the field capital F with this vector v, and that is exactly what you do. That is exactly the concept of a coordinate vector with respect to a basis, or the coordinates with respect to a basis. Okay, so these scalars here, these are the coordinates of the vector v. Okay, so I write this out. These are the coordinates of the vector v with respect to the basis b. Okay, so I have now decomposed this vector v from my vector space into its coordinates of v, its coordinates with respect to this basis capital B. Okay, so I can now describe this vector in my vector space as a n-tuple of elements of the field. Okay, so that's what is beautiful about this, that it allows us to describe the elements of the vector space in terms of n-tuples, these combinations of n elements of the field. Okay, and we're assuming the field is something that we understand and which we've got to find a priori. Okay, right. So what we can now do then is collect these coordinates together into, for instance, a column like so. So I can put C1, C2, all the way down to Cn, like so, and this then is the coordinate vector of this vector v. Okay, so here, this is what we would call the coordinate vector of v with respect to this basis. Okay, and you have to understand that the way that we are ascribing to each element of the vector space a coordinate vector is completely determined by the basis. Okay, our choice of basis, and it's not necessarily true that there's only one basis. There might be many different bases. The only thing that you have to satisfy to be a basis is you have to span the entire vector space and you have to be linearly independent. Okay, so lots of other sets of vectors may well satisfy those conditions, and we could have equally well used those other bases to describe all vectors of the vector space as coordinate vectors with respect to that basis. And that's going to be one of the key messages of this video. Okay, that if you've got more than one basis of your vector space, then you can describe the vectors in your vector space as coordinates with respect to whichever one you choose, and there is no right one and there is no wrong one to use. You can use whichever one you like. That is one of the key messages that I'm going to send here, that you can describe the vectors of your vector space with coordinate vectors with respect to whichever basis you like, and they are all as good as each other and they're all as bad as each other. There's no right one to use. Okay, and that's something that often when people start learning linear algebra they find difficult to understand, and we'll come back to that later on. Okay, right. So what I want to do at the moment though is consider, if we are adding vectors together in my vector space capital V, what does it mean in terms of the coordinate vectors? Can I derive an expression for the addition of two vectors in my vector space in terms of their coordinate vectors? And indeed I can derive an incredibly beautiful and simple expression for the addition of two vectors using their coordinate vectors. Okay, so let me take then two arbitrary vectors. So I've got one here. Here is an arbitrary vector in my vector space, little v. Okay, and you know this could have a horrendous symbol. I could have some silly symbol for this in my vector space, and I've now given it a nice coordinate vector here, which is far more logical because it's just an n-tuple of elements of the field. Okay, now let me take another arbitrary one. So let's take another arbitrary one which we'll call v bar. So v bar is another element of the vector space capital V, and again what we will do is we will describe it in terms of its coordinates with respect to the basis v1, v2, all the way up to vn. Okay, so v bar then, we will decompose it exactly the same principle. So we'll have c1 bar times v1 plus c2 bar times v2, and we'll go all the way on until we get to plus cn bar times vn. So I have expressed v bar then as a linear combination of the vectors v1, v2, all the way up to vn. And these barred coefficients here, these are the elements of the field that I need to multiply the basis vectors by to get the correct linear combination for v bar. Okay, so those therefore are my coordinates of v bar with respect to this basis. Okay, so I'll just write the coordinate vector for v bar then. It's c1 bar, c2 bar, all the way down to cn bar, like so. Okay, and I'll just underline that in pink if I can find the pink pen again, so here it is. Okay, so now let's consider adding these two vectors together in my vector space, and let's try and get an expression for what the answer is in terms of a coordinate vector. So what I want to do is get the coordinate vector for the answer to v plus v bar. Okay, so v plus v bar, again, we have to remember we're dealing with an abstract vector space, so this is defined up here. Okay, it's the addition of two abstract vectors in my vector space. Okay, I would like to make this more concrete by getting an expression for the answer for this in terms of the coordinate vectors of the two original things that I'm adding together. Okay, so v plus v bar then, what is it? Well, what I can do is obviously I can write v as its linear combination of the basis vectors, and I can also do that for v bar. There's nothing wrong with doing that. So I can rewrite this as c1 v1 plus c2 v2 plus all the way up until you get cn vn. So that's v here, and I'll color code it in. So this is our linear combination of the basis vectors that gives v. And then what I'm going to do is add on to this my linear combination of the basis vectors that gives v bar. So I have c1 bar v1 plus c2 bar v2 plus all the way along until you have cn bar vn. Now that's perfectly valid, because if you do actually add both of these things together in the vector space, you will get the exact same answer as if you add v and v bar together in the vector space. So it's perfectly true that that is equal to that in my abstract vector space capital V. Okay, what I can now do is rearrange this to get it as a linear combination of the basis vectors v1, v2, all the way up to vn, and that's exactly what I want, because remember, how do I find the coordinate vector for the answer here? I need to get it as a linear combination of the basis vectors, by definition of what the coordinates actually are. Okay, so I'm going to try and write this as a linear combination then of the basis vectors. So, the first thing then that I'm going to use here is that addition in a vector space obeys the properties of an abelian group, and abelian groups obey associativity and commutativity. Okay, associativity tells me that I don't need to give a monkeys about where the brackets are, okay, which is why I've put absolutely no brackets in here at all. Okay, it does not matter where the brackets are. You can put the brackets wherever you like, the answer is going to be the same, basically, is what associativity tells us. Commutativity tells us that it doesn't even matter what order the things are added in. Okay, so I can swap this one and this one around, and it does not matter at all. So together, associativity and commutativity work beautifully. They tell me that I really do not need to worry about what order things are being added together in. Okay, so I can move them around freely. Okay, so what I'm going to do is I'm going to get vectors involving scalar multiples of the same basis vector nearby one another. So I'm going to get these two nearby one another, these two nearby one another, etc. Okay, so I'm going to rewrite this like so. So I have c1 times v1 plus c1 bar times v1 plus, and then I'll have c2 v2 plus c2 bar v2 plus all the way along until we've got cn vn plus cn bar vn. Okay, so that is a perfectly valid algebraic operation because we insisted that addition in a vector space obeys the axioms of the abelian group, and abelian groups obey associativity and commutativity. Okay, now what we're going to do is use one of the axioms that we insist scalar multiplication obeys, which is one of the distributive properties, specifically the distributivity of scalar multiplication over addition in the field. Okay, so this axiom says that if you have two elements of the field, C1 and C2, and you add them together and get the answer in the field, and then use that answer to scalar multiply a vector v, then it will always be the same answer as if you firstly scalar multiply the vector v by C1, and then add it in the vector space to the vector v scalar multiplied by c2. Okay, and that's a pretty amazing thing that you're insisting is going to have to be true for our scalar multiplication law. Okay, so you appreciate how difficult it would be to build a scalar multiplication law that obeys this, because this addition here is addition in the vector space, whereas this addition here is addition in the field. Okay, so it's not trivial at all that that is true. Okay, so we're going to use this rule in reverse then to factorize out the basis vectors. Okay, so for instance here we're going to factor out v1 and we'll get c1 plus c1 bar, where this addition now is addition in the field rather than being addition in the vector space as it was over there. Scalar multiplied by v1, and then just continuing this on, we'll have c2 plus c2 bar, again in the field, scalar multiplied by v2, and then it'll go all the way on until we've got plus cn bar in the field, scalar multiplied by vn. Okay, so here is our beautiful answer then. Okay, so we've now got the coordinates then of the answer to v plus v bar, because we have got it as a linear combination of the basis vectors, because all of these things here, c1 plus c1 bar, that's just some element of the field. When we add two elements of the field together, we just get another element of the field, and the same for all of these other coefficients. So that then tells us that the coordinate vector for v plus v bar is just going to be c1 plus c1 bar, where this is addition in the field, c2 plus c2 bar, all the way down to cn plus cn bar. So this gives us a brilliant ability to understand addition in the vector space in terms of addition in the field. Okay, so this is why, again, this is beautifully simplifying down vector spaces to just field theory. Okay, so there is what addition means in terms of the coordinate vectors. If you want to add two vectors together in the vector space, just take their coordinate vectors and then just add the different coordinates together in the field. Okay, absolutely beautifully simple. And scalar multiplication is also going to obey an equally beautiful law. Okay, so now let's consider what scalar multiplication is in terms of the coordinate vectors. So once again, let's say we've got a vector v which has a linear combination in terms of the basis vectors c1 v1 plus c2 v2 plus all the way along to cn vn, like so, which means its coordinate vector is as before, the coordinate vector c1 c2 all the way down to cn, like so. And now what we want to consider is if we scalar multiply this vector by some element of the field, what is that in terms of the coordinate vector? I.e., we want to know what is the coordinate vector of this thing scalar multiplied by some element of the field, and is it an interesting relation to the coordinate vector here? Okay, so we are going to consider then our vector v scalar multiplied by some element of the field c. So c is just some arbitrary element of field, and we are now going to scalar multiply the vector v by c. Okay, so what we're going to try and do then is try to write this scalar multiplied vector v by c as a linear combination of the basis vectors v1, v2 all the way up to vn, and then of course we'll have its coordinate vector. And the result is going to be very obvious. Okay, so let's do this then. So we'll have c times this thing here, so c1 v1 plus c2 v2 plus all the way along until you've got cn vn, like so. Okay, so again, that's perfectly true. If you work out this thing here in the vector space capital V, you will indeed get the same thing as if you do this. Okay, now what we're going to do is use another distributive law that we insist scalar multiplication must obey. So another axiom that we insist scalar multiplication must obey is that if you have an element of the field C, scalar multiplying two vectors v plus v bar, so two vectors added together. Okay, so what you're doing here is firstly adding the vectors together in the vector space, and then taking the answer, which is another vector in the vector space, and scalar multiplying it by c. The answer must be the same as if you firstly scalar multiply the vector v by c, okay, and scalar multiply the vector v bar by c, and then add them together in the vector space. Okay, so this is the statement that scalar multiplication distributes over addition in the vector space. Okay, and this is another property that we insist that the scalar multiplication rule must obey if it's going to be considered a vector space. Okay. Right, now we have got a rather sort of bumped up version of this. We've got this on steroids, basically. Okay, but the instant this is true, we can say that this is going to split down into the natural thing. So obviously what we want to say is that this is equal to c times c1 v1 plus c times c2 v2 plus all the way along to c times cn vn. That's the intuitive thing to say, but the reason that that is true from this is that you can continuously break this down into a problem of just having two vectors. Okay, and let me show you how. Consider c1 times v1 as just an individual vector. Consider that as being equivalent to v here. Okay, then consider the rest of this monstrosity, c2, v2, all the way up to cn, vn, as your v bar. It's just some vector in the vector space, so I can consider it as v bar. Okay, then what I can do is apply this law here, which applies for just having two vectors added to each other, to say that this is c times c1, v1, which is what I've got here, plus, what would I end up with? Well, the intermediate bit is I'd end up with plus c times all the rest of this, c2, v2, plus all the way along to cn, vn, like so. But then we can just apply the exact same trick again. We can say, okay, consider c2, v2 as just being one vector, and then consider the rest of it, c3, v3, plus c4, v4, all the way up to plus cn, vn as being the v bar, and then you can split it into c times c2, v2 plus c times the rest of it, and you can just continue this on until you have eventually broken it down into this line that I've got here. So that's why distributivity of two things like this, of scalar multiplication over the addition of two things, can be extended to a distributivity of scalar multiplication over the addition of an arbitrarily large number of things, as long as it's finite. Okay, right. So we can indeed break this down into this thing here. So what are we going to do next? So remember what we're trying to do. We are trying to write this as a linear combination of the basis vectors v1, v2, vn. We're not quite there yet. We've got one more line, because at the moment we've got v1 firstly scalar multiplied by c1 and then scalar multiplied by c. Okay, that's not quite v1 just scalar multiplied by one thing. Okay, but actually it is, because scalar multiplication obeys associativity with field multiplication. So what I can do is rewrite this as c times c1, where this is now multiplication in the field rather than scalar multiplication. Then the answer to that, scalar multiplied by v1, and then I can do the same here, plus c times c2, again this is multiplication in the field, get the answer, and then scalar multiply it by v2, and then continue on all the way up until you get c times cn, again where this is field multiplication, and then scalar multiplied by vn. Okay, right, and then here is our linear combination. Brilliant. Okay, because this is just some element of the field, this is an element of the field, etc. So we've just got a linear combination of our basis vectors, and this is the linear combination for c times v in our vector space, capital V. So what we can now say is that the coordinate vector then for c times v is just c times c1, c times c2, all the way down to c times cn. Okay, and you can see that that's absolutely beautiful, because that means that if we want to scalar multiply a vector in our vector space, what you can do is write that vector as its coordinate vector with respect to our basis capital B, and then all you need to do is multiply all of the coordinates of the vector with respect to that basis by the scalar c, where that's just multiplication in the field. Okay, so again we have reduced a problem which was in the vector space, a problem of scalar multiplication, to a problem in field theory. We've reduced it to multiplication in the field. Okay, and it's reduced to an absolutely beautiful multiplication law in the field. Okay, right, so that is the beauty of getting a basis and then describing all of the vectors in your vector space in terms of that, in terms of coordinate vectors with respect to that basis. okay, that the addition and the scalar multiplication law, which were previously very, very abstract, can now be completely understood in terms of the addition and scalar multiplication laws in the field. Okay, and we'll explore this more in the next video.